Hello and welcome to the full talk about transferring the contamination factor between anomaly detection domains by Shape Similarity. My name is Lorenzo and this work is in collaboration with Vincent Verkluijsen and Professor Jesse Davis. We all are from DTI Lab of KU Leuven in Belgium. But let me start this talk with an overview of the classic anomaly detection setting. Anomaly detection is the task of detecting examples that do not follow an expected behavior. Usually, anomaly detection is tackled from an unsupervised perspective because labels are expensive or difficult to acquire. Therefore, an unsupervised anomaly detector exploits some intuitions to assign anomaly score to each example that represent how anomalous the example is. However, in practice, the anomaly scores are not enough to take decisions, and one needs to set a threshold on top of the scores using either some labels or the domain knowledge. Under the typical unsupervised setting, the common approach is to take advantage of the contamination factor gamma. But in practice, it's the user that has to provide such a contamination factor, being based on domain knowledge. In many practical scenarios, this is not feasible though. In fact, assume now that one needs to monitor a fleet of wind turbines and wants to detect blade icing on each of them. Unfortunately, each turbine has its own data distribution, and especially its own contamination factor. It is unfeasible to think that the user can provide all the contamination factors, especially when monitoring many wind turbines. So our question is, how can we estimate the contamination factor of each wind turbine by only using limited domain knowledge? What we propose is to use transfer learning. Formally, given an anomaly detection model, an unlabeled source domain with its contamination factor, and an unlabeled target domain, we want to estimate the target contamination factor. Essentially, our goal is to transfer such a contamination from the source to the target domain, assuming that the two anomaly detection domains are related. So our main question is, how can we do such a transfer? Well, in this paper we make 4 contributions. First, we introduce the problem of transferring the contamination factor gamma. Second, we propose TRADE, a method that is able to do such a transfer in 4 steps. In a nutshell, TRADE first computes the anomaly scores separately for each domain. Second, sets the threshold using the given source contamination factor. Third, transfer the threshold from the source to the target domain by exploiting the shape similarity of the anomaly scores. And finally, derives the target contamination factor as proportion of scores above the transferred threshold. Our third contribution is the analysis of TRADE's convergence behavior. And finally, we perform an extensive empirical evaluation both on benchmark dataset and on real-world proprietary data. All right, let's now talk briefly about why the contamination factor is actually relevant in anomaly detection. The contamination factor gamma is defined as the expected proportion of anomalies in the data. Its value allows us to set the predictive threshold and transform the anomaly scores into hard predictions. For this task, one can set the threshold such that the proportion of scores above it exactly corresponds to the known contamination factor. Essentially, through the contamination, we know how many anomalies to expect, and we force the model to predict the same number of anomalies. However, one may wonder what the impact of gamma is on the final predictions. Assume that you can collect data from the wind turbine and that your goal is to detect blade icing anomalies. As you can imagine, given a certain wind speed value, the power generated by the wind turbine is lower when some ice forms on the blades. This means that the examples at the bottom of the first plot are anomalies. However, such labels are not known to the detector, as usually labels are difficult to come by. In the plot on the right, we show the results of setting the contamination factor to 3 different values, obtaining 3 different scenarios. In the first scenario, the contamination is overestimated, and the model predicts some obvious normal example as anomaly, meaning high false positives. In the second scenario, the contamination is underestimated, and the model produces false negatives. Finally, setting the appropriate contamination results in the model predictions being correct. But let's now pass to our method TRADE that is able to transfer the contamination factor from 2 related anomaly detection domains. First of all, we want to clearly state and motivate our underlying assumption. We assume that the normal anomaly scores, which are the low scores, follow a similar distribution, where similar refers to the shape. In this slide, we use the same anomaly detection algorithm to produce the anomaly scores individually for each of the 12 proprietary datasets. As you can see from the plot, although different assets have different peaks when the anomaly scores get higher, for the low scores, they show a similar shape. This motivates our methodology to exploit such a similarity to transfer the contamination. But let's now immediately pass to the trade's 4 steps. In the first step, it uses the given anomaly detection algorithm to assign the anomaly scores to each domain separately. In this way, we obtain 2 distributions of anomaly scores. Second, trade uses the known source contamination factor to set the source threshold by forcing the proportion of scores above it to match with the source contamination. By doing this, the detector would make the exact amount of predictions for each class. Once we have the source threshold, trade poses an optimization problem. Find the best target threshold that maximizes the similarity between the shapes of the scores below the thresholds. Essentially, we move the target threshold value and compute the KL divergence between the scores below the target threshold and those below the source threshold. The target threshold value that minimizes such a dissimilarity measure is the one that trade picks. Finally, in the last step, trade uses the same procedure as in the second step to derive the target contamination from the best target threshold. This means that we consider the proportion of scores above the threshold as the contamination factor. However, so far I have never stated what anomaly detector has to be used to compute the anomaly scores. This is because trade is a model agnostic approach, meaning that one can use any existing anomaly detector that is able to assign real valued anomaly scores. Though it may happen that the source and the target distribution of scores look quite dissimilar, which may erode the accuracy of the transfer. To overcome this limitation, we propose to use an ensemble of anomaly detectors that work in 3 steps. First, given an anomaly detector, we estimate the target contamination factor using the previous 4-step approach. Second, we compute the KL divergence between the score distributions of the 2 domains. And finally, we take a weighted average of the target estimates where the weight depends on the KL value. In this way, we aim to make the target estimate smoother and less detector dependent. Our third contribution is a theoretical convergence analysis of trade behaviors to the limit, of course. We started from 2 hypotheses. First, we assume that the source sample is representative of the source distribution, meaning that it is large enough and IID. Moreover, we assume that the target domain could be biased, but when increasing the target sample size, this bias will fade out gradually. The second assumption is that, to the limit, the shape of the normal anomaly scores distributions of the 2 domains is the same. This is just a theoretical assumption that allows us to get our final result. In practice, the 2 shapes do not have to be exactly the same. In a nutshell, the 2 results we achieve are the following. First, the estimated target threshold converges to its real value when increasing the target sample size. This means that our step 3 is theoretically well-defined and sound. Second, the derived target contamination factor estimator is unbiased, which means that step 2 and 4 are motivated as well. I want to conclude this talk with our extensive empirical evaluation. Essentially, we answered 4 questions. Whether our method estimated accurately the target contamination factor, whether such accurate estimate improves the model performance, how an ensemble of detectors perform against each individual variant, and how trade works when varying the source contamination factor. For this analysis, we consider 3 groups of datasets. 12 proprietary datasets on retail stores about water consumption, 2 wind turbine datasets, and 9 public IoT datasets. We consider all the possible pairs within the same group, and we do not transfer the contamination between unrelated domains, say, for example, between a store and a wind turbine, because it never happens in practice. We measure the mean absolute error when estimating the contamination and the F1 score for the model performance. We compare our method with 3 groups of baselines. Source gamma and source lambda use the same contamination or threshold as target estimates. Coral is a domain adaptation method that first aligns the 2 unsupervised domains and then uses the source threshold. Finally, Unify and Otsu use just the target domain and directly estimate the contamination without using any knowledge or label about the source domain. Our first research question is to investigate whether our method estimates the contamination factor better than the baselines. We measure the mean absolute error and the average improvement of using our method instead of each baseline. Therefore, positive values in the plot mean that our method is performing better than the baseline. We aggregate results by target domain, and here, just for clarity, we also aggregate them by dataset group. The plot shows that our method on average estimates the contamination factor better than all the baselines in each dataset group, showing an improvement from around 5% on the stored data till around 80% on the wind turbines data. The second research question is whether a better estimate of the contamination factor improves the model performance. As in the previous case, we measure the average improvement of using our method instead of the baselines. But in contrast with the previous slide, using our estimate produces on average better F1 scores, both in the store and in the IoT data. Regarding the wind turbines, however, our method does not result in greater F1 scores, probably due to the fact that the F1 score value that each detector achieves is quite low. Our third research question investigates whether the ensemble of detectors work better than the individual variants obtained by using a single detector. In this plot, we show the distribution of error between our estimate and the real target contamination factor. Each trade variant is named with its anomaly detector name. And compared to using a single detector, the ensemble method shows lower variance and limited errors, getting errors higher than 0.10 in just a few cases. Moreover, the ensemble variant reduces the error on average by at least 10% and up to 50%. Finally, our fourth research question investigates how trade performs when varying the source contamination factor against each of the baseline. For this experiment, we only use the IoT data and fix the target contamination to 0.01 while varying the source contamination factor from 3% until 25%. Compared to Coral, source gamma, and source lambda, the performance of our method degrades slower when the contamination increases. On the other hand, because Unify and Otsu do not depend on the source contamination, their estimate is not affected by the variation of the source contamination, and therefore our method becomes worse when the gap gets high. In conclusion, we introduce the problem of transferring the contamination factor between related anomaly detection domains. We propose a 4-step approach for such a transfer. We analyze theoretically its behavior and perform an extensive empirical analysis using benchmark as well as real-world datasets. For further information, please check out our paper or use the code available online. And if you have any questions, feel free to drop an email. Thanks for your attention.